Okay, so we're going to do a short lecture here just talking about the atom a little bit further. So up to this point, we know that Rutherford got us to this idea of having a positively charged nucleus. We saw that from the gold foil experiment, and we know the electrons were somewhere outside of the nucleus. However, in Rutherford's model, that did not really explain why electrons never just go inside the nucleus. So today we're going to talk just briefly a little bit about how we actually know how many protons, electrons, and neutrons are, and then you're going to watch a short video to explain our next model, which is the Bohr model. So up to this point, we know that the atom is the smallest unit of matter, and we determined yesterday that every atom is a little bit different, but it has the same stuff inside. So that from our observator disks. What I'm going to add to now, you've done your little investigation to think through the relative size of these things. And protons, neutrons, and electrons are all very tiny, but relative to each other, protons and neutrons are going to be your bigger ones. And we can actually see that here reflected in the size. And protons and neutrons have what are considered to be one atomic mass unit. Now, this is basically a made-up unit that scientists use to describe things on such a tiny, tiny scale. Notice relative to our protons and neutrons, even though the electron actually did have a tiny size, really tiny, compared to the proton and neutron, it does not have enough mass to add to the atom. So that's why we actually say it has 0 atomic mass units. Size is not the same as charge, though. Charge, remember, that's actually an electric charge, which we saw was able to be manipulated by Rutherford. And protons are going to have a +1 charge, electrons have a -1 charge, neutrons have no charge, they're neutral. We're going to get to this a little bit further, this electron cloud idea, but as far as we're concerned with the Rutherford model, that still fits for now. Okay, so these different numbers of protons, neutrons, and electrons, we're going to get into this more as we continue to explore the atom, but I did want to mention right now that this actually is what causes different properties. So when we talked about those families last week, actually I guess it was the week before, those families are going to have different properties based on different numbers of protons, neutrons, and electrons. All right, in your investigation yesterday, you started to discern these things. If we actually look on the periodic table, that number, it's the smaller number, it's usually up top, but it does not have to be, is going to be called the atomic number, and that is always going to be your number of protons. So on your investigation on the last part, you have a little thing of magnesium. If you look at magnesium, its atomic number is not 11, it should be 12, okay? So this is always equal to protons, and it's usually equal to electrons as well because protons and electrons have opposite charges, and most atoms are neutral. We'll talk about cases when they're not, but most atoms are neutral. So when you're just looking at the periodic table, that atomic number is going to always tell you protons and usually electrons. This number at the bottom is, well, or it's going to be the bigger number. It could be at the top. They don't have to be in this order, is your average atomic mass. Now, it is an average because there are different versions of elements that exist, and those things are called isotopes. This is actually an average of all the isotopes that exist. To effectively find your protons and neutrons, you're going to round this average number to the nearest number. In this case, it'd be 23. And then you can actually subtract the atomic number, and that will actually give you the neutrons. So neutrons, you have to do a little more work to find, but you basically take the atomic mass minus the atomic number, and that will give you the neutrons. Again, because this atomic number is always protons. Now I'm going to talk about that average atomic mass a little bit more. So we said before, electrons do not have a mass that we consider when we're talking about the mass of the atom. That means all of the mass we have is inside the nucleus, and that means it's all from protons and neutrons. If we have a change in that number of protons or neutrons, that will actually change our mass of our atom. I mentioned this isotope idea. That's actually where we've added or taken away neutrons from our nucleus, and that will affect the mass of the atom. When you look at the periodic table, that average atomic mass is an average of all of the isotopes that occur, including their relative abundance. Now, what that means is if it's more frequent, then that's going to be taken into account as well. So if you look back at sodium, the most frequent one here, the most frequent isotope is going to be around 23, but obviously there are some that are 22 or less as well. Mass number, that's a little bit different than our average atomic mass that we have in the periodic table, in that it's actually the total number of protons and neutrons together for a specific element. And what that might actually look like, oh, and I kind of already said this already, actually. So again, it just tells us roughly what our most abundant element is when we look at the periodic table. That's going to be the one that's closest rounding. That's usually the most abundant one. Okay, now that mass number that I mentioned can actually be written after the element name, and that can indicate that you have the isotope. And you literally just write the element's name, dash, and then the amount of mass it has. From that, you then can consult the periodic table, and carbon 14 here, if you look on the periodic table, the atomic number for carbon is 6. So you actually, again, can take this mass number, because this is protons and neutrons, take 14 minus 6, and then say, oh, there's 8 neutrons. You can do the same thing with iron, okay? So any element can be written as the element name and then a mass number. We also can always write things in nuclide notation. And this can be for an isotope, or it can just be for a normal element. This is slightly different in that you write the element symbol from the periodic table. So I mentioned carbon 14 already. So the symbol for carbon is C if you consult the periodic table. And in this notation, you actually always write the mass number to the upper left and then the atomic number to the lower left. Okay, so that's always how it's written. This mass number may or may not match the periodic table because, again, remember, this may be indicating an isotope. All right, so just one more example of looking at this nuclide notation. You could write things this way. So here, if we look at protons, neutrons, and electrons are in scandium 46. So again, that 46 is the mass number, so it's protons and neutrons. This 21 is your atomic number, so that is actually telling us how many protons we have, and it will also tell you your electrons because this is neutral. So there, we would just say there's 21 protons, 21 electrons, and then 46 minus 21 would give us our neutrons, which, let's see, that is, what, 25? Hopefully I did the math right there quickly in my head. So 25 neutrons, 21 protons, 21 electrons. There's one more to show you here. So gold, if we look at gold 195, I want you guys to actually do this one. So even though it says example, I want you to actually try that one in your notes. And then one more for you to try here with the nuclide notation, and you're done.